Investigation of Curves, Section 4, Envelopes and Arc Lengths. Video 1, Arc Lengths, Parametric Curves. Before we start looking at how to find arc lengths, let's have a look at the general idea of what it is that we're trying to do. So here is the graph y equals x squared, and a chord has been plotted in red, joining from 0, 0 up to 1, 1. Now this is an approximation, although perhaps not a very good one, to the length of the curve between these 2 points. Now what I can do is, I can increase this value of n here to draw more chords. So for n equals 2, I've joined from 0, 0 to 0.5, 0.25, and from 0.5, 0.25 up to the point 1, 1 here. And the total length of those 2 chords, you can see that it's gone from 1.41 something to 1.46 something here. And I can continue to add in extra chords and subdivide this length up. And as my number of chords increases, the total length of the chords is getting closer and closer to what the actual length of the arc would be. So by the time I've got up to 30 chords here, you can see that over this last little bit, the total length of the chords is really not changing very much to the 4 decimal places I've got shown. And that's the idea that we're going to use. To find the arc lengths, we use a limiting process to subdivide the arc into lots of little chords, and then we're going to look to see how we can use calculus to formalise this and find out what the actual limit is. So let's start with a curve that's been defined parametrically, and we'll have a short section of the curve joining 2 points here and here, where there's a short change in x, which I'm going to call delta x, and a short change in y, which I'm going to call delta y. And because it's defined parametrically, delta x and delta y are both defined in terms of delta t, a small change in t. And our approximation here to the arc length is our chord, which I'm going to call delta s here. Now I can use Pythagoras' theorem, and delta s squared is delta x squared plus delta y squared. So what I want to do is I want to consider what's going to happen to the fraction delta x over delta t and the fraction delta y over delta t if I consider the limit as delta t approaches 0. And this is going to lead to an expression with derivatives ds by dt like this one, instead of my delta fractions here that I had before. So ds by dt all squared is dx by dt all squared plus dy by dt all squared. Now I can use that to find ds by dt by taking the square root of dx by dt squared plus dy by dt squared. And then finally, to find s, I can find the integral of that square root expression with respect to t. Now I do need to be careful and remember that as s is an arc length, it's always going to be positive, because lengths are positive quantities. Let's have a look at how I can apply this in practice. So here's a familiar example, the parametric equations x equals 5 cos t minus cos of 5t, and y is 5 sine t plus sine of 5t. We've seen these in a couple of previous videos. So as before, I put in my computer algebra system x and y. I found the dx by dt and dy by dt. But now what I'm going to do is I'm going to use my formula to find s. So the first thing I'm going to do is to work out the square root. So I want the square root of dx by dt, that's my expression 3, all squared, plus dy by dt, that's my expression 4, all squared. And that's given me this square root just here. So I now want to integrate. So the integral of my square root function in expression 5, and then the limits for my integral are t is going from 0 up to 2 pi. And my computer algebra system calculates that integral to be 40. Now, I can check this by finding a length of the curve in a slightly different way. So going into the graphics window, I've got my function plotted here, and I can use the length function and say the length of my curve, which is called A, from 0 to 2 pi, and then that generates the answer up here, B equals 40. So I've got the answer of 40 in two different ways there. So how would I write this down then? Well, copying down from my computer algebra system, first of all, I want to write dx by dt, which was minus 5 sine t plus sine 5 sine of 5t, and dy by dt was 5 cos t plus 5 cos 5t, and then I write down my formula for s. So s equals the integral from 0 to 2 pi of the square root of, and then dx by dt squared, 5 sine 5t minus 5 sine t all squared plus 5 cos t plus 5 cos 5t squared, and that's all inside my square root, and my integral is with respect to t, and then I can just write down from my computer algebra system that the answer was 40. Now it's worth thinking about other ways we could have calculated this. So instead of doing the whole curve, I could have chosen a section of the curve. So just here, the bit that I'm highlighting in red, we could have worked out what these two endpoints were and done the integral between those t values, and then used the symmetry of the curve to multiply it by 4 and found it that way. Or alternatively, I could have found this section here, or one of the ones like it, and then multiplied it by 6. So if you can spot an integral that you can do with part of the curve and then use the symmetry, you can do that as well. In this video, you've learned how to find the arc length of a curve defined parametrically.